Zach. I'm from Georgia Tech, graduate student there under Amanda Stockton. And today I'm going over some of the more recent data that I've gathered during my graduate career using a system that I built during the early stages using a technology called, as he said, microcapillary electrophoresis with laser-induced fluorescence. And all that is a separation detection technique for organic molecules. And specifically, we tested it using a series of Europa analogs. So to get into it, maybe not. I always like to show this slide because I'm sure you've all seen it, especially in the opening plenary on Monday, but it really puts into perspective how challenging it can be to get to some of these outer solar system locations like or Saturn, I guess this would be Enceladus, but Europa for my case, because it really shows how small, energy efficient, and automated your equipment needs to be. And if you're running any chemical analysis systems, they need to be low volume, simple, high speed, and highly sensitive. And one such piece of equipment that actually fits this profile are microfabricated bioanalysis systems. And specifically, one example of this type of system is our system, the Mars Organic Analyzer prototype. And it was built and prototyped in Mars analog environments. And my advisor was involved in this research under Rich Matthews at UC Berkeley. And they tested it in multiple Mars analog environments, like the Rio Tinto for amines and amino acids in Spain, and found LODs of 75 and 70 picomolar for aldehydes and ketones at the Mojave Desert. And they went ahead and continued analyzing it in multiple other Mars analog environments, like Bumpus Helen, Atacama Desert, for other different types of organic acids. For this talk, I'm specifically focusing on amines and amino acids for characterizing my system, and not in a Mars environment, but a European environment. And I think all of you know probably at this point why Europa is so important, and it's, in general, there's a lot of water there, and we're trying to get towards the more subsurface water, or at least some of these cracks on the surface, because on Earth, we see that our oceans are just teeming with life, particularly down in the bottom near the hydrothermal vents. So this is a really great target when looking for organic biomarker molecules. So to get into the technique itself, we use a microdevice, a pretty simple design here with a T-cross channel, so you can generate an injection and a plug right at the junction, and then send it down your separation channel with some patterned U-channel bends to generate an effective separation distance of 6.7 centimeters. So it's a very small platform for running these analyses with this microdevice. And to briefly explain how that phenomenon works, if you were here for Peter Willis's talk, he went over this, but to briefly go over it, in that capillary, you have a stacked layer of positive charges using your analyte, and when you apply voltage to it, you generate a current down that capillary, and you can actually separate out positive, negative, and neutrally charged species using combined EOF and electrophoretic flow. And you can take advantage of this fact by generating an injection at your T-channel at your junction by inducing this current down from your sample to your waste, and then shifting your currents so that you pull back towards your waste and your sample and start moving your analytes and molecules that you're looking at down towards your detector. So now moving towards the detection technique, for amines and amino acids, like I said, what we're dealing with, for the ones we were looking at, they're not innately fluorescent, so we need to attach fluorescent probe, and we use Pacific Blue succinylmonoester that's been shown to work very efficiently for the amines and amino acids using systems like this at buffer pH of 9. And it's a very simple reaction, it's very fast, takes about 15 minutes to go to nearly completion. And so we like to use it as our lab standard for amines and amino acids. So you can imagine, like I just showed here, you have your detector here. As it's going down this column, it reaches your micro device, which is this tiny little dot here, that's your channel. And when you're shining a laser on it, it generates the fluorescent signal, which is captured by your system. And to briefly go over the design of the system, we have a laser here at 405 nanometers, which is excitable for Pacific Blue succinylmonoester, going through a long pass filter through a dichroic mirror into your objective lens, which focuses it onto your micro device channel. And then you can capture the fluorescence back through your objective lens, down through your dichroic, through a long pass filter, through a spatial filter off of a mirror into a focusing lens, and then eventually into your detector. And for our case, we use a spectrometer. And to put that into a picture to show what all these components are, we have our 3D stage, which allows us to, this differs from most breadboard systems where you physically mount all of your lasers and your equipment onto the breadboard itself down here. I did a 33 millimeter cage cube system inspired from Aaron Noel at JPL. And so we are actually able to move our entire optical assembly wherever we want it to go to align it to our microdevice stage at the top. And to point out some of the major components again, we have our laser and all of our mirrors and filters to our objective lens, and then bring down our fluorescent signal back to a fiber to our detector. So we characterize this system using a set of standards and buffer concentrations. So first we wanted to take a look at the effect of buffer concentration using our specific microdevice. And we did a series of concentrations and found that 35 millimolar was ideal for running our separations before Joule heating occurred. And Joule heating really will generate bubbles in your channel and it will affect your separation significantly. So to be safe, we went with 35 millimolar boric buffer for our continued experiments. We ran LODs of alanine and glycine and found the LOD of our system to be 2.2 and 2.91 for alanine and glycine respectively, which is on par with other systems with spectrometer as a detector. So to get back to Europa, we then needed to characterize our system for Europa analogs, not just basic lab standards. And we know that Europa has magnesium sulfate, sodium carbonates. So we took a look at those, and we also wanted to take at a more benign situation with carbonic acid and a more extreme situation with sulfuric acid to analyze the effects of pH. So to start off, we have our separations of carbonic acid. So what we have here as going down, it's a decrease in concentration of your nasty stuff in solution. So in this case, carbonic acid. Starting at 2 nanomolar, which is about as concentrated as it gets because it's pretty weak and it's hard to get concentrated. And this dilution up here represents a dilution before reaction. So you imagine you have this 2,000 nanomolar solution of carbonic acid diluted 1:1, so it's actually 1,000 nanomolar. And what we see here is that no concentration, not even the high ones, affect our separation, and basically we can generate every reaction and every separation is exactly what we were expecting. So weak acids don't have an effect on our CZE separations. So we moved on to sodium carbonate Europa analogs, and what we started to see is some of the higher concentrations. And so this is the same experiment, just done with a different analyte here. And some of the higher concentrations started to show effects in our separation. So we went ahead and diluted them further. So what these show, the fluorescence intensities along this axis are scaled relative to each other. So this is a 1:1, this is a 1:10 dilution. These fluorescence intensities are scaled 1:10. So that's why it seems a little more noisy here. But what we see here is as we begin to dilute our solution and dilute our sample, our analog sample before analysis or before our reaction, we begin to start seeing our peaks even at the higher concentration sample. So there actually are organics in there. You just need to dilute it beforehand because you're having effects from sodium concentration in your solution, creating ionic dispersion effects affecting your injection. Moving on, we went to take a look at sulfuric acid. So this is an extreme acid case. And so we were seeing that, in fact, we were basically even at the low concentrations, it was affecting our injections or our separation or reactions. And so we started doing more dilutions and then more dilutions. So 1:1, 1:2, 1:10, and 1:2 started making it a little better, and 1:10 really was more ideal. And in contrast to the sodium, which was affecting our separations due to ionic dispersion effects, this was affecting our reaction because, as I alluded to, because reaction with Pacific Blue and organics is pH dependent. So the high concentration of sulfuric acid was creating a low pH in your analog sample, which was not allowing your reaction to occur. Moving on from that, we took a look at magnesium sulfate Europa analogs, and basically this was a worst case scenario, but you can fix the deleterious effects of magnesium sulfate, which is affecting your injection, by adding in EDTA to sequester any metal cations that it can chelate, and just bring back all of your separations and organic peaks immediately, up to about double the concentration of EDTA in there. which is about 5 millimolar. So does that summarize it down there? Moving on, we analyzed an Earth analog sample provided by Kate Kraft, one of our collaborators at Johns Hopkins Applied Physics Laboratory. And we know here that this geyser at the Champagne Geyser at Chaffain Ranch in Utah actually has carbonates and sodium chlorides, and it has high ejection pressures analogous to plume ejector or subsurface ocean pressures. So we went ahead and analyzed a sample here, and what we saw is that we ran a 1:40 dilution of the sample, and we spiked for our other series of organic acids, leucine, valine, serine, alanine, and glycine, which we've done before. And we saw nearly all of them except for the 2 acids in the sample. So if you take a look from the bottom up, we run our standard just to compare to every time so we know our separations are working really well. And then we run a blank just to see what no signal would look like. It's really hard to get alanine out. It's Earth. There's a lot of life here. It's hard to get rid of all the organics, even if you 10 times distill your water, 50 times distill your water. So taking a look at the sample itself, we clearly can see alanine. There's tons of alanine everywhere, as we would expect, because we can't get out of our blank. But we also spike in and can see our leucine, valine, serine, and glycine, and then various other organics that we have yet to identify, but we have other standards that have been done before we can compare to. And our spike sample, we can quantify some of these organics using spike standards, and in fact, we quantified alanine and glycine to fairly high concentrations, so 875 nanomolar for glycine and 80.1 micromolar for alanine. So that concludes some of the work we did for our Europa analogs. I just want to summarize some of the major accomplishments of the project. So first and foremost, we have a 2.12 nanomolar limit detection for our benchtop system, and as I said, that's analogous to other similar systems built with a spectrometer as a detector. We have successful separation series of sulfuric acid, carbonic acid, sodium carbonate, and magnesium sulfate Europa analogs to demonstrate the robustness of our technique towards these types of environments. And we detected organics in a Utah geyser sample analogous to that of a Europa analog. Our future work, I hope to do, is to run some automated processes of these analyses using a microfluidic processor. And as well as not listed up here, I would like to start building a more miniaturized system of this type of micro CELIF system. And I actually do have the components in lab, so I just started building it right before coming here, so I'm pretty excited about that. That system uses a PMT as a detector, so I should be able to drop the limit of detection from nanomolar to picomolar, at least 1 order of magnitude from our preliminary experiments. And of course, I need to show my acknowledgements here. So I have so many collaborators everywhere that I'm so fortunate to have. So I just wanted to point out all of them here. At Space Sciences Laboratory that I've been working with for a few years on an Enceladus Organic Analyzer project. JPL, a lot of the people here were provided some of the initial insight for the project 4 years ago. Of course, Berkeley, Richard Matthews, and Martin Gulazar, which I worked with out there. Kate Kraft for providing the sample and her IRAD team at Johns Hopkins. And my funding sources, NASA, Georgia Tech, NSF, and the Center for Chemical Evolution. And I just wanted to point out that my advisor has a talk tomorrow if you're interested in analogs research, and it's Friday at 11:15. Thank you.